All right. So when the bases are the same, you simply we will compare exponents directly. Okay. I'm gonna show you. I'm gonna write something that might seem kind of abstract here, but it's going to be the rule or the guidelines that we use all the time for these exponential equations. If I start with, let's just say our base is b, and then I raise that to, I'm just going to say f of x. Okay? So that might be, when I say f of x, that's just another expression. It might be like 2x. It might be 2x plus 3. It might be just 5. Whatever, I could put another algebraic object up there in the exponent. Does that make sense? Okay. The next thing I'm going to do is say, so our equation is going to be if b raised to the f of x equals b raised to the g of x, okay, if that is happening in front of us, okay, then the way we solve that is that we make the conclusion that f of x has to equal g of x. And what that will do is it will ultimately get us away from looking at the bases of b and just focus now on the equation that is established when we look at the exponents and compare the exponents. So I'll give you an easy kind of start to this with an example to hopefully validate that statement. Okay, so let's start with a base. Let's say our base is 3. We'll say 3. So let's just go 2x. Okay, so that's exponential. That's an exponential equation because the variable is now in an exponent, right? Okay, let's say that is equal to 3 to the 8th. Okay, so can you see, I'm just going to color code these. Can you see that right there is now that specific 3 to the 2x? Okay, this right here is this specific 3 to the 8. So in our specific example, what would f of x be? If we look at this yellow stuff, what would f of x be? Okay, f of x is just this numerator, or sorry, this exponent right here, right? So isn't this exponent right there just the f of x? So if this is what's happening, then to solve it, we're going to say 2x equals g of x. But if I look at g of x right there, that should correspond to that 8, right? Does that make sense? Everybody see that comparison? Does that let you solve for x now? What's x got to be? Okay, so divide both sides by 2, I should get x to be 4. And now think about this. If I put 4 in, go back to your original equation, put 4 in for x, you would have 3 raised to the 2 times 4. What's 3 to the 2 times 4? It's 3 to the 8, right? Does that make 3 to the 8 equal to 3 to the 8? Yeah. Okay, so that's how we solve exponential equations when the bases are the same. All right, so let's go through. What I want to do is I want to go through a series of examples here because they don't always end up being that easy. So we'll try to build to some more difficult ones, but let's go. What? But I agree with that to an extent. But if I want to use this stuff in real-world scenarios, remember go back to that question where we asked Ella if she wanted to buy a $50,000 Jeep and she had $3,000 and how long it was going to take her to let that money sit in an account? It did. It was like 150 years. Okay, so if I want to figure things out like that, which are a lot messier, then I need to have some type of ability with more complex equations, because this is just a general statement for all of mathematics. If the math is going to be applicable to the real world, which that's why we learn the math, because it is. Okay, math is what makes everything in the world work. It's what makes us understand everything in the world. Okay, the world can be a messy place, therefore the math is going to be messy when we use it to understand those things. Does that make sense? So the messier the math, the more applicable it usually is. So I want to build some of that difficulty here. So let's just do this one. Let's say we have 2 to the 5x plus 4 equals 2 to the 3x plus 1. All right, so first thing we're going to do is look to see if the bases, we know it's an exponential equation, and this will be, you'll run through kind of a hierarchy of decisions every single time you see an exponential equation. You'll ask yourself, okay, are the bases the same? Because that's what we're hoping. Are the bases the same? That's the hope, because if the bases are the same, what can we do with the exponents? Compare the exponents. Compare that blue thing to that blue thing, right? So we're going to go 5x plus 4 should equal 3x plus 1. So go ahead and solve that equation. Subtract 3 from both sides, or 3x from both sides. Then subtract 4 from both sides. Then x will be negative 3/2, right? Go back to a concept that we've talked about multiple times. Let's take this equation. Let's take 2 raised to the 5x plus 4. Well, so what Desmos was doing there, if you were seeing, I couldn't put plus 4. It would always drop it down to the base. So if you have an exponent that is a quantity, you need to put in parentheses for Desmos to understand it. So that is the left-hand side. The right-hand side we had as 2 raised to the 3x plus 1. Okay? And now the answer to this problem is where those things intersect. And we can see it, they intersect, they cross right here at negative 1.5. Negative 1.5 is, as a fraction, negative 3/2, right? Okay? Or you can do it this way. You can say, I want that to be, instead of using x, I can use, like, call it a, call that a, and then say a equals negative 2/3. Negative 2, or sorry, it was negative 3/2, my fault. Negative 3/2. And now you see that they evaluate to give me the same y value of 0.088. And that can be a way that we could check to see that we've done it correctly. Does that make sense? Okay. Questions on that format? Looks pretty straightforward. Let's do this. Case 2. Bases are not the same, but 1 can be restructured to make them the same. So this is something like maybe we say we have 9 to the 4x equals 3 to the 16th. Okay, so we see it's exponential again, right? Exponent has or carries the variable, but because the bases are different, so previously the technique we were using earlier, it's called a one-to-one correspondence, and you've used this before. This is considered a one-to-one correspondence. The only way that these two sides are going to be the same is if that is the same as that, because these are identical. You've seen this with fractions before. If I say that I have like x over 5 equals 4 over 5, this is a one-to-one correspondence. The only way that I can make this left-hand side identical to this right-hand side is to make x turn into what? X turn into 4. That's called a one-to-one correspondence. Okay. Then I could cross multiply and all that kind of stuff and solve for x, and it gives me 4. But that one-to-one correspondence is nice. Same thing happens here. This is a one-to-one correspondence here. So the only way that I can make this true then is if these two things are the same. That doesn't exist here yet. Okay? Because these are not identical, so we cannot say that those are identical. Does that make sense, everybody? Okay? But this is where laws of exponents are so pivotal in everything that we do. Can I make 9, can I rewrite that so that it is a base of 3? Okay, so 3 times 3, but now let's, because it's going to, so the way I would have to do that is I'd have to have 3, okay, so what you said first was 3 times 3, and the way that I have to write that would be this way, and that's going to be messy, that's going to be confusing, okay, but actually let's go with this, because I think we can do this. Do you guys remember, and I don't know if it's going to be insightful, but it should work. If I go, you guys remember saying like A, B, some product raised to the n power, and we rewrote that as A to the n, B to the n. We're doing that, okay? Because that's a 1, and that's 1. Basically, you just distribute that n to those exponents. Can I do that here? A is this 3, B is this 3. So I can rewrite this as 3 to the 4x times 3 to the 4x, right? What do I do with exponents? What do I do with exponents when I have bases the same and I'm multiplying? I add them. So this becomes 3 to the 4x plus 4x, right? Well, what's that the same as? 3 to the 8x. Okay, so that's what we want this to become. And now that, I don't want you to go through that approach that we did in red there, because that's messy. What Maya then said was she changed what she said. She said, instead of writing it as 3 times 3, let's write it as 3 squared, right? So if I write this as 9 as 3 squared, I should still have this 4x right there. Does that make sense? And now that's a power to a power. So you multiply the exponents now, and I get 2 times 4x, which is now what? Still 8x. Okay? So either approach is okay. I think the power to a power is better. Okay? So I get 3 to the 8x equals 3 to the 16th. Now, what do we know about our bases? They're the same, so the exponents then must have to be the same. And we can solve that and get x to be 2. Okay. Now, I don't know what I would assume 3 to 16 is going to be okay. It's going to be small enough for the calculator to do it. Sometimes checking these, if you're using like a TI calculator or just a cheap like Walmart $10, $15 calculator. Well, in respect to other calculators you can buy, you could spend $1,000 on a calculator. It's going to do a lot more than what and it's going to be more powerful than your $10 calculator. So the cheaper your calculator, what I'm trying to say is that it might not be able to calculate something that large, okay, with some of the exponents that we do. But 3 to 16, this calculator will do it, okay? Sometimes your calculators, because of their memory, their RAM, which costs money to make, won't allow you to do calculations at a certain threshold, okay? But now so 3 to 16 gives me that. Now if I go 9 raised to the 4, and we found x to be 2, right? So 4 times 2, I got to put that in parentheses. Now I can just type it in as 8 if I wanted to. But does that give me those two things to be the same now? 3 to 16, the same thing as 9 raised to the 8? All right, so that's the idea that we get when we talk about changing things to different base, or changing one of our bases so that they're both the same. Now, here's what kind of stinks about this, is that they use some common values a lot that they think are just common knowledge for a lot of people. So I'm just going to show you, like if I took, let's just say, let's see here, take 2, let's do it this way. I'll just say value, and then we'll go to value squared, value cubed, value to the 4th, value to the 5th, okay? So what they'll do is they'll assume that you know a lot of these relationships. So I say 2 as my value, and then I say 2, and we'll actually go A1, A2 squared equals A2 to the 3rd equals A2 to the 4th equals A2 to the 5th. All right, good. So a lot of times that they assume that you're going to know that I'm only going out to the 5th power here, but a lot of times they're going to assume that you are able to see that when they say, you know, one side is going to have a base of 3, and they write the other side as a base of 243, that you know that there's a base of 3 existing in that 243, okay? Which is, I think, maybe not the best assumption that they make, okay? But that is something that they do regularly, okay? So basically saying, do you know that relationship between those ordered pairs, or those, not ordered pairs, but those values? Do you know the relationship between those values, those, and so forth, all the way through, okay? So maybe a table like this would be nice to have in front of you when you're doing some of these initial problems. So let's do one like that. Let's say, if I say 5 raised to the 7th, or 7 plus, let's go 2x, equals, let's go 625. Something like that. Okay? Now here I don't have, and on the right-hand side, all the other ones we've done so far were on the right-hand side, or one of the sides, we've had always an exponent. Now 625 does not have an exponent here, other than 1. Okay? You can put it there if you want. But the structure looks a little bit different, because all the other ones both had exponents that were algebraic or non-trivial. Okay? This one's a little bit different. Still approach it the same way. We want to see if we can create a base that's the same. Does anybody know the relationship between 5 and 625 in terms of powers? What's 5 squared? 25. Okay. What's 25 times 5 again? 125. What's 125 times 5 again? 625. Okay? So that's what I'm trying to get at, is that when we see things like this, okay, and a lot of times they'll be fair to you. They'll try to use a number that, that's a prime number. So then the only way that I can really make these bases the same is if I take 5, raise it to the first, 5 to the second, 5 to the third, 5 to the fourth, and try to find out when do I get 625. Okay? Or they'll make it a small, like, even number, and then we can work. I'll show you an example of what I mean by that here in a moment. But they'll try to be at least fair in some manner to you. But if I look at this, this would be the nice thing to having this table. If this column here is the base column, I see 5, 625. That's to the 4th power. Okay. So now I can rewrite this as 5 to the 7 plus 2x equals now 5 to the 4th, right? Thanks. Now, because the bases are the same, what can I say about those exponents? Bases are the same, exponents have to be the same, right? They're comparable. Okay, so 7 plus 2x is equal to 4. I'll get 2x is equal to negative 3. X in is negative 3 halves. And again, if you're ever worried, did I do everything right? Do I have the right answer? Plug it back in. Put negative 3 halves in up there for your x. So negative 3 halves times 2 is negative 3. What's 7 plus negative 3? Careful, 7 plus negative 3. 4. So when I plug negative 3 halves back in here, this goes 5 to the 4th. Is that the same thing as 625? Yes, it is. Okay. So that's nice. So let's go a little bit further. And I'll try to make this example a little bit more difficult, but not as difficult as we can get. Let's go. We know our powers are 3 very well. Let's go 3. Let's rewrite. Let's go 9. Let's go 9 to the 2x equals. Let's go 243. Let's do this. I can't. No, let's go. Sorry. 9. Let's go. I'm thinking. I'm sorry. I'm sorry. Well, if I type, you don't have to use them if I type them out. I'm just trying to benefit those people that want them. Okay, so if I look at those, that's 27. So which one is this? I think it's best to always look at the smallest base. So what's the smallest base up there? 9. And now if I go 9 to the first, that would be 9. What's 9 squared? 81. So that already exceeds the 27, right? Huh? X plus 1. So I can't rewrite 27 so that's a base of 9, right? Okay. This is a situation where I've actually have to alter both bases. What is a common? Oh, that'd probably be unappropriate. So what would that number be? 3. Okay. So if I look at the way I do it, I don't know the correct nomenclature, the correct terminology there, but I can see that when I look at 9, I can rewrite 9 so that has a base of 3, and that would be 3 squared, right? So 9 is 3 squared. How can I rewrite 27 so that it has a base of 3? Three times 3 is 9. Times 3 again is 27. Okay? So 3 squared is 9. 3 cubed is 27. And that, again, would maybe be a benefit of having this table, right? Okay? So, right now all I've done is I've replaced that 9, so I still have to have that 2x. And here I still have to have that x plus 1. Okay? Now, what do I do when I have powers to a power? I multiply. So this is going to give me 3 to the 4x, right? Okay. What changes size on me? 3 to the 4x. Now, here, you're going to have to multiply as well, right? But 3 is a singular value, and x plus 1 is a quantity, right? So what am I going to have to do with those when I multiply them? You have to distribute them. Good. Okay? So this is going to turn into 3 to the 3x plus 3. Okay? Now, are the bases the same? Yep. So what can I do with the exponents? I can compare them through equality. So 4x equals 3x plus 3. So what's x going to be? X is going to be 3. Okay? Now, we've done a lot of work there, so I'm going to go back to Desmos and see if that works. If I type in 9 to the 2a and type in 27 to the a plus 1, okay, now if I make a go to 3, does it give me the same result? Those are the only two, that is the only value in which those two exponential expressions are equivalent to one another. Okay. You guys feel comfortable with a little bit of this? Your homework is going to ask you towards the end of it, there's 10 questions. Towards the end of it, they're going to ask you to utilize your knowledge about these things. Okay? So, what's that? No, I haven't signed it yet. I'm going to send this to you in your email if you want to use this tool. Okay? And actually, I'll just make it. Huh? Why can't you get your email? All right, so I'll put this on Schoology now. No problem, sister.